Let's start talking about that. Okay, so we'll get rid of all these guys here. So we're supposed to write a method that adds two fractions together and returns the result in reduced form. A fraction should be represented as a two-bucket integer array. All right, so in our little example here, a fraction might be int array f is equal to 1/2. Int array f2 is equal to 1/4, something like that. And now we want to have a method that's going to, so we'll make it static. It's going to return an integer array called add fractions. And this guy will take an integer array A and an integer array B as a parameter. Okay, so he's going to take two fractions in as inputs, add them together as fractions, reduce them, and return the result as a fraction, or representation of a fraction. Okay, so if I have the fraction 1/2 and the fraction 1/4, the first thing we need to do is get a common denominator, right? So the common denominator we need to get is we're going to multiply the denominators by each other to give us an 8. All right, so the first thing I'm going to say int common denom is equal to A at bucket 1 times B at bucket 1. That's the denominators from those two fractions. Okay, so that would be the 2 and the 4. So here, I'll go ahead and make our call to this. First of all, class method or instance method? Class method. How do you know? How do we call class methods? It's the name of the class in which the method was defined. So we'll say add fractions. We'll pass it f and f2. So f and f2 are the two fractions I'm passing into this particular call of this guy. F will come in as A. F2 will come in as B. So when I say A at bucket 1, that's going to get me that guy. B at bucket 1 will get me that guy. This is bucket 0. This is bucket 1. Okay? So this is taking the two denominators and multiplying by each other. Okay? Then I need to say int new num1, new numerator, let's say, is going to be equal to A at bucket 0 times B at bucket 1. Make sense? Okay, so we're going to cross multiply. So that'll take 1 times 4. Int new num2 will be B at bucket 0 times A at bucket 1. All right, then our new fraction is going to be so int array answer is going to be new num 1 plus new num 2 and then common denom. This won't be reduced yet, but it'll be at least an added fraction. All right, then we'll return our answer. All right, now we need to quickly give ourselves the ability to display a fraction. I think I may have had that in there before, but whatever. So this is going to be static void display fraction. This will take an int array f as a parameter, and I'll say system.out.println f at bucket 0 slash f at bucket 1. So kind of a nice way to print fractions out. So if we say driver.display fraction f, that should show us 1/2. f2 should show us 1/4. And then we might say int array f3 is equal to the answer of that one. and then we can display F3. So we run this, we get 1/2, 1/4, those are our, that's F and F1, or F and F2, whatever. And then F3 is the sum of those guys non-reduced right now. So that gets us our 6/8. That makes sense? So that's the first part of the assignment. Okay, because assignment requires us to now reduce that fraction. So I'm going to write another method. We could certainly do it inside of add fractions, but I'm going to write a method called reduce. So this guy's going to be a static void reduce, and it'll take an int array f as a parameter. And the job is to reduce f to its lowest, to reduce the fraction. Find the greatest common divisor of both the numerator and the denominator. Okay? Why did I not return a value here? Because ultimately what I'm going to do here is I'm going to say this, driver dot reduce answer. And then I'll return answer. So assuming reduce works, I don't have any logic in here, but assuming this works, I'm going to pass a fraction in and it's going to reduce that fraction. But I'm never actually returning a fraction. I'm not printing it, I'm returning it. It's passing the address. So to show you that, and it's purposely why I wrote it this way. So let's do this. Let's say I have the fraction 6/8. I'll just put that in a text box thing here. So there's 6/8. Actually, it's in an array, right? So 6/8 will just represent arrays like that to keep it easy. So 6/8 lives somewhere in memory. All right, and right now I have a variable called answer that points to this guy. In memory. So answer actually has a value associated with it, which is a memory address. So maybe this is memory address 55, and then this guy actually lives at memory address 55 in memory. But of course, memory addresses are always green, so it's the okay, so answer is a variable which holds a value. The value it holds is a memory address, which points to a place in memory, which actually has the fraction that lives there. That make sense? Okay, what actually lives here is an array, a 2-bucket array, so it actually is memory address 55 and then some more memory, but this is good enough for this example. So that's what we're dealing with right here. I have a variable named answer, and it points to a place in memory that is that fraction. Okay? Right here, I'm passing answer into my reduce method, which has a local variable called f. So now I have a variable called f inside of the reduce method, a variable called answer inside of the add fractions method, and both of these guys actually point. They both hold the same memory address and point to the same exact value in memory. Make sense? So if reduce makes some changes in here, changes that guy to 3/4, won't answer now point to the 3/4? Yeah, because it changed it in memory. That's why I did not have to return a value. Nothing had to come out of here. It's going to actually change it down here. So if I just, for right now, say f at bucket 0 is equal to, actually let's just do f is equal to 3/4. Oh, it's gonna be. I want to trick you, but I'm trying to decide the best way to trick you. Nah, just leave it alone. So this will be 3. This will be 4. And that's all this guy is going to do in this particular example. We're hard coding it. We're not actually doing the reduced fraction math, but we're just hard coding it in here. So now whenever we call reduce right here, we're passing answer, the pointer, the answer by address into F. F now points to the same exact place in memory as answer did. That's this scenario right here. Then we're going to F and we're changing it from 6/8 to 3/4. We're just overwriting those values. And then that method ends. So reduce is now done. So now we're back. We just finished this line right here, and now I go to return answer. And when answer returns, it's returning a pointer to answer, which points to this place in memory, which has a 3/4 there. That make sense? We did not have to return the array because we were actually manipulating the stuff in real memory. All right. So now let's, here, I'll run it real quick.
Excuse me, is there any disadvantage if we did return a new array?
Return a new array or just return F?
Return F.
Okay, so we're going to say this guy's going to return an integer array. And we'll say return F here. And then down here we'll say answer is equal to the result of driver.reduce answer, like that. It'll have the exact same result, we just wasted our time. Because what we did is as we called this, we passed answer in as F. We changed F locally. Then we returned answer, setting answer equal to whatever fired out of that function, which was F. So now answer points to the exact same place it used to point to. So we effectively just overwrote answer with the same value that used to be there.
So it's just insufficient.
Inefficient. Yeah, inefficient. It'll be the exact same answer. That's like saying int a equals 5, a equals 5. Okay, but now we actually need this guy to do the real math for us. We'll switch this back to void. This concept here is an important concept to understand side effect. So when you're passing stuff around by address, changes that you make are permanent changes. Okay, when you're passing stuff around by address, changes that you make are permanent changes. Okay, so what we need to do, and we're going to do this we're going to hard code this the first way. Well, not hard code. We're going to do this the inefficient way initially, because that's what you wrote your paper on, and we'll talk about that a little bit. So we started off as 6/8 here, right? So I want to figure out how do I reduce 6/8. In order to reduce a fraction, I need to find the greatest value that evenly divides both the numerator and the denominator. Correct? Okay. So one way I could do this is I can start at the smaller of the two values. Correct? So I can figure out which is smaller, the 6 or the 8. If the 6 is smaller, then that's the maximum value that could possibly evenly divide both values, right? Biggest value that could possibly divide both of them. In this case, we know that's way too big, but we'll just deal with it, okay? So the first thing we're going to do is we're going to figure out which is smaller between the numerator and the denominator. And we're going to store that inside of a variable called max. So the output here would be, if we create a variable called max, after we look at these two guys, max is going to be equal to 6. The smaller of the two, numerator and denominator. Whichever one of these guys is smaller is the maximum value that might evenly divide both values. Make sense? All right, so we're just going to ask a question and we're going to create some memory. So we'll say int max is equal to f at bucket 0. So we'll assume that the numerator is the smaller of the two. Then we'll say if f at bucket 1 is less than max, max actually equals f at bucket 1. So we are just assuming bucket 0 will be the smallest. Then we'll ask the question, is bucket 1 actually smaller than bucket 0? If it is, replace max with whatever's at bucket 1. So after this little, so this is creating memory. This is asking a question. All right, right back to our bread and butter, the way human beings solve problems. So now when we get to right here, we know max holds the smaller of the numerator and denominator. And we're looking for the largest value that evenly divides both the numerator and the denominator. So we know the biggest is going to be 6. So we're going to say, does 6 evenly divide 6? Sure. Does 6 evenly divide 8? No. 6 becomes 5. Does 5 evenly divide 6? Nope. 5 evenly divide 8? 4 evenly divide 6? 4 evenly divide 8? Yes, but it's got to do it for both of them. 3 evenly divide 6? 3 evenly divide 8? Nope. 2 evenly divide 6? 2 evenly divide 8? Yes. Finally, we hit a double whammy, right? Got them both. So we are going to start at max and walk down to 1. We know that 1 will evenly divide both of them, correct? It's like the rule of math. Okay, rule of math. Every number is evenly divisible by 1. Makes sense? Well, every real number is evenly divisible by 1. All right, so we're going to have our loop that's going to take a max on a voyage between 6 and potentially 1. That makes sense? Now, how many times are we going to have to spin? What's the maximum number of times we have to spin? 6 times? Okay. What's the minimum number of times we might have to spin? Okay. So now all you have to close your eyes, and you're gonna reach in and grab a fraction out of a bag. I'm gonna ask you, tell me, how many times do I have to spin through the loop to reduce this guy? But you're not allowed to look at your fraction. You don't know. Somewhere between 1 time and max times. Correct? Somewhere in there. So this is actually kind of an interesting dilemma with this one, because you ask yourself, which is the correct loop to use for this? Is it a for loop or is it a while loop? We know for a fact that we will be counting from 6 down to 5, down to 4, down to 3, down to 2, down to 1, and somewhere in there we might stop. Okay? But we know all the values we're going to count. Similarly, we also know that we will eventually hit a value that evenly divides both of them. Right? So we could also do this in a while loop and just say keep going until, keep reducing max until we finally get a number that evenly divides both of them. That make sense? So let's look at both of those. So let's do the while loop first. So I'm going to say while f at bucket 0 mod max is not equal to 0, or f at bucket 1 mod max is not equal to 0. Okay, so when I take the numerator, I divide it by max, and it's not evenly divisible, or the other one's not evenly divisible if at least one of these guys is not evenly divisible by max. What do? I say max minus minus. When I get past this loop, max will be the greatest common divisor of the numerator and the denominator. Okay, so the first time through, max is 6. Is 6 evenly divisible by 6? Yes, that's true. Is 6 evenly divisible by 8? It's not. So this will be the false, because it is evenly divisible by it. It's not evenly divisible. This will be the true. So we have false or true. Uh-oh. No, that is true. So what should this be? Both of these conditions. Both of these conditions need to be true in order for the whole thing to keep spinning. I need to find if max does not evenly divide this guy and it does not evenly divide this guy, I need to try a different max. That make sense? So, if the current value of max does not evenly divide this guy as well as evenly divide this guy, it might evenly divide one of them. But if it doesn't evenly divide both of them, I need to try a different max. So the first time through, does 6 evenly divide 6? It does, so this will be false. Does 6 evenly divide 8? It does not, so this will be true because it's the not equal, right? So this is false and true, which will be false. Max minus minus. 5. 5 evenly divide 6? Nope, so this is our true, right? 5 evenly divide 8? Nope. So what's that going to be? So now we have true and true.
Yeah.
Ruh-roh. That's not what we want either. So what should this Boolean expression be? I want to keep reducing max until I find a value of max that evenly divides both the numerator and the denominator. We're very close with what we have right now. Oh, so you want to change these to equal equal? So this says as long as the numerator is evenly divisible by max and the denominator is evenly divisible by max, subtract under both circumstances. So we start off at 6. Is 6 evenly divisible by 6? Yes, that's true. Is 8 evenly divisible by 6?
No.
Nope. So this is true and false, which is false, so we'll fall past. Haven't got the correct max yet. So we need to construct the appropriate Boolean expression that is true as long as both the numerator and the denominator are not both evenly divisible by max. So as long as at least one of them fails the test, as long as at least one of them is not evenly divisible, we want to keep spinning. Because we need to find the situation. We don't want to exit this loop until we have a value of max that evenly divides both. We were closer when we had it like this. When is this current Boolean expression true? Let's think about the truth table for this current Boolean expression. Okay, when both sides are true, and both sides are true, when what happens? Well, no. Under what circumstances are both sides of the and true? The numerator is not evenly divisible by max. And, so that's the one side, that's true, right? So if the numerator is not evenly divisible by max, we'll have one side of the and be true. If the denominator is not evenly divisible by max, we'll have the other side be true. Okay? So, numerator is not evenly divisible by max, denominator is not evenly divisible by max. As long as both of those things are true, try again. Right? Okay, but what do we really want to say? We want to say as long as at least one of those guys is not evenly divisible, we want to try again. As long as one of them is not evenly divisible. Let's go back to our OR. So this guy will be true if either the numerator is not evenly divisible by max or the denominator is not evenly divisible by max. Right? Is 6 evenly divisible by 6? It is. So this is false. Is 8 evenly divisible by 6? Nope. So that's true. False or true is true. And what do we do when a Boolean expression is true? Keep spinning. So max is now 5. 5 evenly divisible by max. I'm sorry, is 6 evenly divisible by 5? No? So that's going to be a true. Okay. Do we even need to check this other side? No, because we know it's false right here. Okay, so since we don't need to even check the other side, this guy boils down to true because this part right here. Okay, so that means we're going to spin again because it's true already. Now max is 4. 4 evenly divisible, or 6 evenly divisible by 4? Nope. So this is true. So we're going to spin again right off the bat. 3. 3 evenly divisible by, is 6 evenly divisible by 3? Yes. Is 8? Okay, so this is false or true. So max minus minus. So now we're down to 2. Is 6 evenly divisible by 2? Yes, that's false. Is 8 evenly divisible by 2? Yes, that's false. False or false is false. So the loop is now over. That make sense? Okay. Why didn't you think that was right to begin with? That's what we wrote at the beginning, isn't it?
Because it's a bit, there is a not equal to, so
Okay.
it's got a bit tricky.
Yep. So you need to make sure that you fully resolve Boolean expressions. You have to fully resolve Boolean expressions because this guy might look like one thing, but when you actually resolve the Boolean expression, it comes out to something different. Okay? There's something called a truth table that you could create. You could create a truth table associated with this guy and say, when this side is true and this side is true, this happens. So you could really give yourself almost a plug and chug and then just see the situations where this thing is false. All right, so this while loop's going to keep whittling down max. When we're done here, we're going to say f at bucket 0 is equal to f at bucket 0 divided by max. F at bucket 1 is equal to f at bucket 1 divided by max. And that's it. That's all reduce does. We don't have to return anything. It's just changing it in real memory. That make sense? So we add, we call our reduce. What does our reduce do? It figures out what's the smallest of our numerator and denominator. Then it whittles down max until we finally get to a common, the greatest common divisor of both the numerator and denominator, which we know will eventually be a 1. So we know as humans that we will exit this loop. Okay, otherwise, this could be an infinite loop. Correct? But we know we're going from, in this case, 6 to 5 to 4 to 3. When we get to a 1, this loop is guaranteed to finish at a 1. We know that, not Java. Okay? Then we'll divide the numerator and denominator by the appropriate value. And we get our 3/4. All right, so now we can give it all sorts of different, so we can call this guy 5/16 and 3/22. Add these guys together and we get 79 over 176. That's the reduced fraction. Make sense? Does that seem right? We had to come up with a common denominator between those guys. So 22 times 16 was 352. 176 is not so bad. All right. Now, how could we have done this with a for loop instead of a while loop? Right? So do you understand how this while loop's working? When you're trying to decide what kind of loop to use, you're going at it from the perspective of, okay, well, do I know how many times I need to spin? In this case, the answer to that is no. You sort of know how many times you need to spin, right? But it also is a counting problem, which lends itself to a for loop. So not knowing how many times I'm going to spin lends itself to a while loop. Counting problems lend themselves to for loops. Is this more of a counting problem or more of a I don't know how many times I need to do this problem? Okay. Probably more of a counting problem. I think that's fair. Because I know I'm going from, in this case, 6 down to 1. That sounds like counting to me. Okay, so this probably lends itself to a for loop. So what we're going to do here is we're going to say for int I is equal to max, I is greater than or equal to, well actually it's not even that, let's just say greater than 0, I minus minus. All right, and then what are we going to do? If f at bucket 0 mod max is equal to 0 and f at bucket 1 mod max is equal to 0, if both of those things are true, we have found the greatest common divisor, right? So we'll say f at bucket 0 and set it equal to f at bucket 0 divided by I. F at bucket 1 is equal to f at bucket 1 divided by I. But now we don't want to go through this loop anymore. So we need to get out of the loop. Okay, have we talked about breaking here? I'm stuck in the loop. That'll break us out of the loop. Oh, I'm sorry. So now I is 0. Is 0 greater than 0? It's not. So the loop will break out of the loop the next time naturally. So we set a trip up here, right? How many of you use break? Nobody use break?
We can use return as well, right? Return.
You could technically use return. Not a bad solution. So you actually could do this. We have looked at the return keyword. What does the return keyword do? It makes the method immediately end. If you have something after this, it'll return that value as the return type. This guy has a return type of void. So using return semicolon just makes this method end. That makes sense? So this is a nice little shortcut of just saying, okay, I've done what I needed to do, bye. Kills the method. Make sense? So another trick you could use, and we see this guy still front row. Change max with I? Here? Started I off at max. Keep going as long as I is greater than 0. Oh. You want to say max minus minus. There? Oh, mod I. Because max stays the same the whole time through. I is what keeps changing. There we go. Now we got the same value. All right, so there's the for loop version of this guy. All right, now, so is that the solution to the homework? Programming assignment? Okay. Now, tell me what you found out about time complexity problems. Because we have one right here, but we're not really seeing it because our computer's fast enough to make up the difference. We can almost try to fake it. Let's say I do And I can't tell if that was faked a little bit or not, but you know, let's assume that went a little slower. This is argument, okay? All right, but certainly if we're going to do this a whole bunch of times, it starts becoming a problem, right? Okay, so let's well, we'll look at an example here in a few minutes. So tell me what you found out about time complexity issues in your paper.
We use big numbers. It'll take more time if you go that way.
Okay, so the bigger our numerator and denominator are, the more time it's likely going to take to reduce the fractions doing it the way we're doing it, right? You know, because if the smaller of your two values is, let's say you have, 3.8 billion as one of your as your numerator, and 2 as your denominator. All right, and you're going to pick the smaller of those two. That's going to go fast. Okay. What if you have 3.5 billion and 3.6 billion? Okay. Now you got to walk down 3.5 billion numbers potentially until you find one that evenly divides it. Now, when you have a number like 3.6 and 3.5 billion, you're going to have to go down a whole bunch of numbers before mathematically it's even possible for one to evenly divide the other. That makes sense? So we're needlessly checking, in this case, billions of numbers. Okay? So time complexity issues deal with math problems that on the surface do not seem to be difficult, but under the hood actually have quite a bit of math that's having to happen. In this case, we said there's going to be 3 billion values that we have to check. That makes sense? Okay. So what do we do about time complexity problems? Just ignore them?
More efficient algorithm.
Come up with a more efficient algorithm if we can find one? In this case, we have one handed to us, and we'll look at it. Okay, but first we want to see this guy be weak. All right? Because if we were to write the greatest common divisor function here, we're not going to notice. It's not going to seem like it's a big deal, right? Okay, first thing I'm going to do, just to give ourselves a little more wiggle room, is I'm going to change our fractions to be longs. Just so we have a little bit more, a little bit larger value we can work with here. Okay, that should be good there. Add fraction, we're taking in a long A, long B. These are all longs. And this guy's going to return a long array. Okay, so this allows us to have larger numerators and denominators.
What about the F2 and F3?
Yep, these guys will have to be. So now let's go ahead and give ourselves some bigger values. Well, see, actually, we can't use that syntax because this syntax takes in 2 integers. So we actually need to use the just to keep ourselves sane. Let's do it this way. I'm going to introduce a new class to you. So we have a class called big integer. So the big integer class, and if you remember way back when we were talking about primitive types, we talked about the byte, short, int, long, okay? And when do we use each of those? Well, when you need to hold a bigger number, right? Each of them holds a range. Well, what if you need to hold something that's longer, that's bigger than a long can hold? Well, that's when you use something else. There's an object type that's part of the language. It's given to us in the language called big integer. And big integer allows us to hold arbitrary sized integers. Does not matter how many digits are in the integer. Now, the bigger the number, the slower the performance of the big integer class. But it will allow us to have an infinite precision number. Make sense? As far as your computer has memory. All right. So what we're going to do is we're going to re-implement everything we've just written, but using big integers. Before we do that, I'm going to take you to the big integer documentation so we can practice using that a little bit. So java.sun.com is the documentation website. We'll go to Java SE over here, Java APIs. All right, and I believe big integer is in java.lang. It is not, so it must be java.util. It's not. Where is... Here's big integer. Oh, java.math. That should have made sense. All right, so it's in java.math. When in doubt, just click on all classes and just search through the gigantic list of all the Java classes until you find what you want. When you click it, it'll tell you where it's actually located. This guy's in java.math. Okay, so here's the reference for this class. All right. So we can build a big integer out of a string. We can build a big integer out of a byte array, all sorts of different stuff. We could have also done this with our radixes. Could have helped us in our previous assignment. All right. So this will effectively convert from a value that's well, integer.parseInt does this too. This would convert from if I passed it a binary number here as a string and passed it a radix of 2, it would give me the integer decimal value of that as a big integer. It would do the conversion for me. Okay, but not important for us. We're interested in this one. So when we build big integers, we're going to pass it a string representation of the number. So if I want to hold the number 123, I'll pass it the string 123. Okay, that's how I hold that big integer. Now, big integer has a whole bunch of stuff available to us. We can add big integers. We can multiply big integers. Okay, so just as a general rule here, here's the add. So big integer, add another big integer. Is this guy a class method or instance method? Instance method. How do you know? No static. Okay, so that tells us about the type of class this guy is. He's filled up with a whole bunch of instance methods. So in order to use these methods, we're going to have to create instances of big integers. Make sense? All right, so let's go ahead and convert all of our current code to big integers. So this is going to be big integer array f. And let's see if this syntax will actually allow us to do what I want it to do. New big integer So we'll go back to our 1/2. It's going to want us to import java.math. All right, then we have our big integer f2, and this guy will be a new. There, you copied it, right? And here. So we'll just go back to our original example, the 1/2 and the 1/4, just to test it. Then display fraction. This guy's going to take in a big integer array. And actually, out of curiosity, real quick, I don't think we need to do anything else for that. Yep, 1/2, 1/4. Big integer already has the ability to convert itself into a string displayable value. We'll talk about that when we start talking about objects. There's a good reason for this, but just pretend like it's just okay. It's okay for right now. All right. Our answer is going to come out of here as a big integer. Add fractions is going to take in two big integers. Or big integer arrays, rather. Then we're going to have a big integer common denom, which will be A1 dot multiply B at bucket 1. So this guy right here is whatever lives at bucket 1 of A. A is an integer, or is a big integer array. So what lives at bucket 1 of A will be a big integer. So here's a big integer who is calling his multiply instance method, which takes another big integer as a parameter. All right, so this is equivalent of saying A at bucket 1 times B at bucket 1. But this is how you do it with big integers. Because the multiply sign, the asterisk, doesn't support, it's the primitive type arithmetic operator. It doesn't support objects. So I can't take one big integer and add it or multiply it by another big integer. I can't say this. Because this guy is an object type. This guy is an object type. Each of these guys is one of these dudes. He's not an int. He's not a long. He's not a double. He's a big integer, which is an object. This arithmetic operator is only defined for the primitive types. Byte, short it, long, float, double, blah, blah, blah. Make sense? All right. So if I need to multiply these two big integers by each other, I have to use the multiply method provided as an instance method inside the big integer class. So if we go look at that method real quick, scroll down to multiply. Returns a big integer. It's called multiply. Takes a big integer as a parameter. No static, so it must be an instance method. How do we call instance methods? Using an instance of the class in which it was defined. So this guy right there, it's easy to say, oh, well, that's array looking. Well, this says go to the memory address associated with A, go to 1 times the size of a memory address, offset into memory. Get me the value that lives here. That's what that basically says. Get me the value that lives at A at bucket 1. And the value that lives there is a big integer. So this guy right here is an instance of the big integer class. And an instance of the big integer class is allowed to call big integer instance methods, like multiply. Make sense? The multiply method requires that I pass it as a parameter, another big integer, or to multiply by. So I'll pass it another big integer. That is the big integer found at B at bucket 1. So this is going to multiply these two guys together, producing a brand new big integer, which I'll store in a variable named common denominator of type big integer. Similarly, I'll have a big integer, new num 1, and this will be this guy, dot multiply this guy. Then I'll have big integer, new num 2, and it will be this guy, dot multiply, dot multiply this guy. And then our answer will be a big integer array. New num 1 dot add new num 2, which will produce another big integer. And then common denom, which is already a big integer. So we're going to have a big integer array called answer, Bucket 0 of that will be the sum of these two big integers. Bucket 1 of that will be the big integer that we already calculated up here, common denominator. All right, then we're going to call our driver reduce. Reduce needs to take in a big integer. We're going to figure out which is the maximum value. So we'll start max off at the first big integer. Then we need to be able to compare big integers to other big integers. So we'll say if f at bucket 1 dot is a let's just look at the documentation. I thought there was a less than and a greater than, like LT and GT. So absolute value, add, and bit count. This guy's going to come in handy in a little bit. Yeah, I think we're going to have to use max and min, because I don't think we have the... Yeah, we don't. That's okay. This will actually be easier. So we'll say that big integer max is actually f at bucket 0 dot min f at bucket 1. So the name of my variable is called max. I could call that elephant if I wanted to. But this is the maximum value that would be a common divisor of both. This is the min function, which is an instance method of big integer. So this is saying f0, call your min function, pass it f at bucket 1, and this guy will boil down to the smaller of f0 and f1. That's what min does. Show you the documentation for it in here. Min returns the minimum of this big integer and val. That is the big integer that called it, and val, the big integer we passed it. It'll return the smaller of those two. So it's exactly what we did before, except we didn't have to use the if statement, and part of it was because they didn't provide us with an ability to say less than or greater than. I really thought that used to be there. What if they took it out of the documentation? I must be wrong. I don't think it would have come out that quickly. So anyways, after this line of code, max will be equal to the smaller of these two numbers. Okay, then we're going to start big integer I off at max. Keep going as long as I, how do we say greater than? Oh, interesting thing here. Prime numbers, maybe you read about it when you were doing your paper on time complexity. Calculating prime numbers is another time complexity problem. If you want to generate a gigantic prime number, it's incredibly complex to do that. In fact, a lot of our modern math algorithm or encryption algorithms are based on the difficulty of extracting two prime numbers out of one number. So if you take two big prime numbers and you multiply them together, good luck getting those two prime numbers back, making a guess at what those were. It would take like thousands and thousands of years. RSA is the encryption algorithm that's based on that. Let's see, can I fake this a little bit, I think. First of all, let me show you a couple of these fields up here. Big integer has some static fields to represent a 1, a 0, and a 10. If these would become handy, and we're going to use the 1 for 0 here in a second. So what I'm going to say is we're going to start big integer I off at max. Keep going as long as, what we want to say is we want to say I is less than, or I is greater than 1, right? Well, we can say greater than 1. Once it gets to 1, the answer is already what it was. We don't need to check anything greater than. We know at 1, it'll evenly divide, but we know it won't change. So if it's 5/6 right now, 5 divided by 1 is 5, 6 divided by 1 is 6, 5/6 is 5/6. Okay, so we want to say that it's greater than that. So what I really need to do is
You can use the static 0 method.
I think I can say I dot minus, or is I dot subtract maybe? I dot subtract big integer dot 1 dot equals big integer dot 0. Keep going as long as that's not true. So we're going to take our current big integer. We're going to subtract from that a 1. So when it finally gets down to 1, 1 minus 1 will be 0. Okay? So if this is the big integer representation of 75, 75 minus a 1 is 74. Is 74 equal to a 0? It's not. So we're going to keep going as long as 74 is not equal to a 0. That's what that not at the beginning is. But when we do get down to a 1, so when I is 1, 1 subtract 1 will give us a 0. Is 0 equal to 0? It is. That's true. Not true is false. That'll make this loop end.
You can also say the minimum between this number and 1 is not equal to 1.
Actually, if we assume it's always positive, couldn't we also say this? Keep going as long as I is not equal to big integer dot 1. I think that basically says the same thing that I just said, but in a far less cool way. Far less cool way. So yeah, we'll just go with this. It'll be accurate enough for us. So this is saying keep going as long as the current big integer, our current count, is not equal to a 1. And what do we want to do each time? We want to subtract 1 from it. We're going to say I is equal to I dot subtract big integer dot 1. Now notice I said big integer dot 1 here instead of I dot 1. Why is that? If we look at the documentation, here's this field. Is this a class field or an instance field? It's class. Don't worry about whether it's a method or a field. Fields are variables, methods are methods. But the idea of class versus instance is the same. Since this guy has static out front, this guy belongs to the big integer class. So this is like a constant that's part of the class. So an easy way of accessing a 1, a representation of a big integer for a 1, is just saying big integer dot 1 because it's owned by the class. That make sense? So each time through, I'll set I equal to, what I is my big integer, whatever it currently is, minus a 1. Okay? Then, we do have a modulus operator. So we're going to say f at bucket 0 dot mod I dot equals big integer dot 0. I'm actually going to steal this and just change the f at 0 to f of 1. Okay? So if that's true, we just converted the exact same code. So if f0 mod I is equal to 0 and f1 mod I is equal to 0, then we're going to set f0 equal to f0 dot divide I. And f1 equal to f1 dot divide I. All right, so that's reduce. Easy peasy. The funny thing is this does nothing more than what our previous solution did, except it supports much larger numbers, so that we can actually view our time complexity issue. All right? But this is still an interesting concept. So do you understand how we've just taken this brand new thing I've shown you and used the documentation? And because of the way we understood the difference between class methods and instance methods, what does static mean? What does the absence of static mean? Having those couple of things in our memory allowed us to very easily read this documentation. Initially, documentation is usually pretty intimidating to look at. And even for most of you, this is going to be intimidating. But when I actually zeroed you in on something, and I said, is this a class method or instance method? Is this a class field or an instance field? When you just looked at this rather than viewed this thing as just a wall of text, it wasn't difficult, right? You were able to look at it and say, oh, well, how do I call this guy? Here's the equals method. Well, wherever we are, let's just go up to add. Here's the add method. Class method or instance method? It's an instance method. How do you know? No static. How do I call it? I call it using an instance of the class in which it was defined. What class was it defined in? It was defined inside the big integer class. How do I call it then? I call it with an instance of big integer, and I have to pass it a big integer, and it's going to be, and the result it's going to spit out is going to be a big integer that is the result of the big integer I called it with and the big integer I passed it, added together. Does that make sense? Okay, we don't have to know how it works under the hood in order to use it. Say we went to Home Depot and we bought a new leaf blower, and it's a lot like our old leaf blower, but our old leaf blower doesn't blow leaves anymore. So we got a brand new leaf blower, and it has a couple extra buttons on it and stuff like that. We don't know what they do yet, but we'll figure it out. Okay, but we know how to use this leaf blower because now we know how to use leaf blowers in general. We learned on the previous leaf blower. And even though this one's bigger, better, badder, and solves a different problem, because it can blow leaves now across the street or something, so it's your neighbor's problem, you still knew how to use the leaf blower because of your previous knowledge of leaf blowers. We know how to use the documentation because of our knowledge of how class and instance methods are defined. Make sense? So, say this again.
In the help file, a concrete method.
Oh, go all the way down to the bottom. Actually, I don't think there actually are any of them. Concrete methods are, in the context of this, would be abstract methods. Methods that cannot change. We'll talk about abstract, but that's the best answer I can give you right now. Okay, but it's a method that cannot change. For right now, we know about static and instance methods. Okay, these guys kind of come through something else called an interface. Not very important for us right now, but all you really need to know about is class and static and instance methods. It is funny how they call these static methods, they call these instance methods, where really this is a class method and this is an instance method. But I suppose Perhaps calling it a static method makes more sense, just from a learning it perspective, where common object-oriented programming methodology would say that, or I guess nomenclature would say that static methods are owned by the class, therefore they are class methods. Instance methods are owned by instances of the class, therefore they're instance methods. So, yeah, whatever. Okay, so then add fractions, we call our reduce, and ultimately we're going to return a big integer array. So now we've gone through and we've converted everything to big integers. We're initially having 1/2 and 1/4. We're adding them together. Well, we're going to display the two fractions first. Add them together through our add fractions. Add fractions comes and does all the same stuff it did before, but does it in terms of big integers. Calls reduce, which does the same thing it did before, but does it in terms of big integers. And ultimately, we return our new answer. We're going to store it inside of F3, and then we're going to display F3. Okay. Now, we made a whole bunch of changes, and I'm sure they work, so we don't have to test it, right? All right, there's our 3/4. It's a dice roll. All right. Important thing to understand here is we just objectified our primitive version of add fractions. But we've only gone halfway. By the end of today's class, we will have written our own objects. Okay? So, we're done with this easy crap. Gotta go to hard stuff. Hopefully what you're seeing so far is every single week, things aren't getting easier, but the things that you're doing are harder, but the things that you're doing you believe are actually more complicated, but they feel about as hard as what you did the previous week because you're getting a little bit better. Is that a Viking shirt?
Yeah. Uh-oh.
Oh my gosh. How long have you lived here? A while, haven't you?
15 years.
Were you from Minnesota initially? Oh, I guess she has an excuse. I'm from Illinois, and I'm not a Bears fan. Oh, those are the worst kind of fans. The worst kind of fans are the fans that only are fans of a team when the team's good. No. Bears fans should be proud to be a Bears fan, regardless of how bad the Bears were last year.
Maybe 30 years ago. Yeah,
There's nothing wrong with the Bears. Everything's cyclic, right? Bears probably shouldn't have fired their coach. They did. So now they got stuck with the guy who took the job got stuck with a team that just wasn't prepared to play good football. Packers are actually, I think, a pretty, regardless of how well they perform, I like the way their program is run, where they kind of get draft picks and just keep them for their whole career. I just think that's interesting. And there was an interesting fact of the early last season when the Packers played the Bears the first time, that it was the team with the least number of players that have played for other teams, the Packers, against the team that has the most number of players that have played for other teams, the Bears. So, well, the Packers won this year. But the Packers had a good team this year. The Bears didn't have a good team this year, so you'd expect the Packers to beat them. It's just a bad deal. Well, then you see her Vikings team. You got a team that was a really solid team until they lost their main weapon, their running back, and it looks like he's not coming back.
Yeah.
The guy,
They're down there wooing him right now.
that's kind of terrible. I think. I'm not a.
I don't blame him. It's cold in Minnesota.
Well, I guess what I'm saying is, no, obviously, I'm not going to condone. I'm not going to condone him, beating his kid or whatever. You raise your kid the way you want, and if this was anybody else, it wouldn't have made national news. So, but that has nothing to do with his ability to play professional football and beat up on other men, right? Those are independent things, I guess. But I guess you have a franchise, and they have to make decisions that make the franchise look like they're not supporting something. So I don't know, but You guys are probably not going to be a very good team for a while because you spent a lot of money bringing that guy.
Yeah, well, we're
So.
rebuilding.
Yeah, it's hard to replace arguably the best running back in the league.
Well, at least we got a decent
Certainly top
quarterback
three.
now.
Top.
We have a decent quarterback.
Oh, sure, but quarterbacks are a dime a dozen.
Not decent ones.
I would say decent quarterbacks are a dime a dozen. I don't think so. If we're going to say Aaron Rodgers is a good quarterback, I don't know that you can take a very good team with a poor quarterback, put Aaron Rodgers on that team, and have that team be Super Bowl contenders next year. I don't think the quarterback makes as big of a difference as people think. He's the showman, but everything's about the defensive line. Well, the offensive line, first of all, to make sure the quarterback survives. So the better your offensive line, the better your quarterback tends to look. So if you take, really the Packers have a mediocre offensive line, but if you put Aaron Rodgers behind a really strong offensive line, so this guy has a week to throw every pass, I think he'd be pretty good. But you put him behind, a Pee Wee Football League's offensive line, Aaron Rodgers is going to dislocate his shoulder in the first quarter. It's going to be the way it goes. See, all because she wore a Vikings.
That's yours. Uh-oh.
Yeah, I didn't even follow the NFL before I moved here. I've been here, so this is my 9th year here. And when I went to get my driver's license, they made me sign a waiver saying I'd be a Packers fan. I think they were kidding, but that was funny. So I find I have become an NFL fan now. I follow the Packers and stuff. I don't care, right? Who wins. I almost like the people watching after a loss or a win. You watch the next day and the whole city's depressed. Like right after the NFC championship game. The people say, "Oh, we should have won." No, you didn't finish playing the football game. Yeah, you beat them for 95% of the game, but whatever. So the better team won. Fine. But man, listening to Packers fans make excuses the next day, just love that. Just love that. Huh? Yeah, but Wisconsin people can hold their booze pretty well. They sober up quick, especially in something. Yeah, especially. So, I don't know, but I find I'm still not a baseball fan though. I can't stand watching watching Major League Baseball. It's just too slow for me.
They're speeding it up this year.
Are they?
They're trying to.
But it's really funny though, because when I was a kid, I was a huge baseball fan. I used to collect all the baseball cards and stuff like that, and then and I wasn't a football fan at all. In our house, we were tennis fans. So my dad was a tennis fan. So my brother and I, we were big time tennis players. I broke my back and got fat. That's a whole other story. But once upon a time, I was a very good tennis player. But in any case, so now my top sports, I want to say I probably watch NFL more than I watch tennis now. I watch the Grand Slams for tennis, but my primary sport I watch is golf. I'm a very,
Even without Tiger?
huh?
Even without Tiger?
I'm a very avid golfer. So, I like watching, I'm a pretty good golfer. So I like kind of the science of it and stuff like that. Sure, I like watching Tiger Woods. You want to see the best players in the world play, right? But I really like when you watch them on the course, seeing what decisions they make from different positions. What's the shot they pick here? Are they going for the shot that has the 1 in 10 chance of success? Or are they taking their chances with a bogey or something? So I kind of like the mental aspect. In some ways, golf is exciting from that perspective because it's almost like somewhat physical chess. But I can tell you one thing. With people who say golf's not a sport, the positions those guys put their bodies into, you look at Tiger Woods, that's the whole reason his body's breaking down. You might say old man golf on the golf course with some beer is maybe marginally a sport, right? They're drinking some beer, they're swinging some clubs and stuff like that. But the athleticism these guys have to put their body into the position they have to get it into to hit the ball as far as they do is ridiculous. I'm a pretty good golfer. I don't hit the ball as far, not anywhere near as far as the pros, but I hit like 250 yards off the tee or 260 off the tee. Not bad. And I've been on one of these machines that shows you your body positions compared to the pros. So it shows you like your shoulder turn. I'm a lefty. And my shoulder turn is like 30 or 40 degrees short of what some of the pros are. Like not even close. So I don't know. I just find the physics and almost the chess playing aspect of it just fascinating. Tennis is more real-time golf, because tennis you have to react. You can't plan things out. You can set up, for being a tennis player, I know you set up points. So I might drive a couple of balls down the line, then go cross court. Then when he's chasing, I might rush the net to put a volley away to the open court. You kind of set him up for that. So there's a strategy from that perspective. But it's so real time, you're just reacting. But every sport has its little things like that. And until you get into the sport, you don't appreciate it. So I don't really watch NASCAR, but my friend, my neighbor who goes to my church is a big NASCAR fan. So I'm thinking, okay, well, how hard can it be just to drive around a track? Right? Yeah, turn left, whatever. But now, the reality is once you get into it, there actually is quite a bit of stuff they're having to do. When do you take a pit stop? When do you not? How much fuel do you take on? Because you basically want to finish the race on fumes. There's all these things that they have to kind of guess with to make the right decisions. And I don't know, I just find it interesting. There's typically way more strategy to sports than people tend to think there is. So I guess whatever. Okay, so we just tested this and it's working, right? So this guy's now working for small fractions. Now let's give it some big fractions. All right, so we gave it a big fraction. Run this guy. Our reduce is still cooking. No, it's not done yet. Still going. Yeah, these are just our numbers we're adding. Yeah, we created two big integer-based fractions, printed them out. No, it's still cooking. It's still working on our fraction. We just added two fractions together, and now we're reducing it. Okay. Okay, and how big are these numbers? Really big? All right, fair enough. Well, remember our common denominator is going to be this guy multiplied by this guy.
How do you know that it's still running?
Little red light here.
Where? Oh,
This
there.
guy, and we don't have our answer. Two evidences. Yeah, we only have our first two numbers printed out. This is fraction. This is F1. This is F2. We're waiting on F3. We don't have the answer yet. How long do you think it'll take?
Forever.
Until the end of our break.
Maybe for days.
I bet you it will take longer than that. My guess is this will probably take, and I'm just making a guess, and it's really a shot in the dark. This will probably take at least 5 hours. Just watch it finish right now. It's just a pure liar. Okay, it's really a shot in the dark because it really is going to be a measure of at what point was it evenly divisible by. But the punchline here is think about how many numbers do we have to burn through? How many quadrillions of numbers do we have to burn through before we even get into the realm of the numbers that are evenly divisible? That might be evenly divisible. Right? Okay? So this is doing a lot of work right now.
How about changing the number, making it smaller, like 2-3 minutes?
Well, I would be making a guess. Yeah, I promise you this is working.
Something not huge, I think.
Oh, we already showed this works. We showed this works. I promise this is working. If we leave this running, whether it's tomorrow or in 3 or 4 days, it will pump out an answer. Okay? It will. I promise you. All right? This is a time complexity issue. Okay? Giant numbers, trying to add them together, reduce the fraction. If I just add these together and spit it out and I don't reduce, this will run fast. Or at least substantially faster. So here, we'll take out the reduce. We'll run this. Done. Here's the unreduced fraction. Oh man, look at that denominator. I mean, this is, what is that number? That's 1. So that's 100,000, that's millions, that's billions, that's trillions, That's quadrillions. That's quintillions. That's septillions. Sestillions. That's septillions. That's octillions. Ay, ay, ay. No, it keeps going. Just I don't have the numbers. Yeah, is it nanillions? Maybe nanillions? I actually wrote a app for it's. I wonder if it's still on the App Store. I think it's just called Big Number. Oh, there it is, Big Number. We'll download this and I'll have it read our number to us. So this app I wrote this years ago. So you're gonna have a much younger version of my voice. It's on the App Store. It's just called Big Number, and you can type in any number. And what I did is I used voice splicing, and it's my voice, but it'll actually read the entire number out. So, I don't know, this will be kind of entertaining. It's about halfway done downloading. So here, let me just, for right now, is that the bigger of the two? Well, whatever, this is big enough, right? That's big enough. So let me just store this in a text editor real quick. Just so when this is done, I can type it in. All right. So we'll leave that guy cooking. Now, just real quick, let's go back to our reduce. We know this is a problem, right? Reduce takes too long. We're going to change our reduce to say static void reduce to. And this guy will take in a big integer array f. But this guy's going to use the greatest common divisor. Okay? So what we're going to do is we're going to say big integer GCD is equal to f at bucket 0 dot GCD f at bucket 1. We'll actually look at the algorithm here in a second. We'll just use the built-in one here. All right, and then we'll say f at bucket 0 is equal to f at bucket 0 dot divide GCD. F at bucket 1 is equal to f at bucket 1 dot divide GCD. All right, so this is our new reduced fraction. Now, trust me, GCD is doing something. It's doing an algorithm. So we're just taking advantage of something that's already written. We'll actually look at Euclidean's algorithm here in a second. But we just want to see, here's the first version. This is just using reduce. Okay? So give it 20 seconds, blah, blah, blah. It's a problem, right? Yeah. Okay? Now let's just change it to reduce to. Done. A lot quicker. So if you take my estimate of even 24 hours, which it could have easily taken that long. My estimate of 24 hours, that was instantaneous, right? Using Euclidean's algorithm. So Euclidean's algorithm look at a generic one here. And we'll see kind of how it works. You could have written it yourself, but this is what's in the here's an implementation. So when we pass in so Euclidean algorithm takes in two values, and it's going to give us the greatest common divisor of these two values. So we have an integer a and an integer b, for example, or in our case, a big integer a and a big integer b. And we're trying to determine what the largest value that evenly divides both of these is. So we have a while loop because we're going to keep whittling things down. We don't know how many times we're going to have to do this, but we're going to keep doing it over and over again. So as long as our second number is not equal to 0, we're creating a variable called t, we're preserving the current value of b inside of t. Then we're setting b equal to a mod b. So what we're doing by that is we're taking huge swaths of the numbers we have to look at out of the equation each time through. Okay? A couple minutes ago we talked about that, we have, 4 quintillion plus numbers that we have to walk through that are completely a waste of time. Now what we're doing is we're taking these giant leaps through the numbers based on integer remainder of 2 divisors. The idea is that for A and B to be evenly divisible by something, one can't be sufficiently large that it would not divide into the other one itself. So we need to keep shrinking them down together in order to get to something that's even a realistically possible divisor. All right? So that's why we keep modding. We're taking advantage of this idea of long division, where we take a number and divide it by another number and we see how much we have left over. If what we have left over is bigger than the original number for the old one, well, then it's impossible for the next time around for that to divide into it. Okay, so this allows us to keep, this is more than halving our numbers in most of the cases. So this whittles down those quintillion numbers or whatever down into substantially smaller steps. That makes sense? So when we were going through this thing, let's say a quintillion times before, maybe we're going through 5 times now, taking big steps like this. Okay, because it allows us to target in on what are potential common divisors. Okay, potential common divisors. Not checking every number to see if it might fit into the square-shaped hole. All right, so each time through, we preserve the current value of B, we overwrite B with A mod B, and then we set A equal to the old value of B. So we're taking both numbers and cutting huge swaths out of them. All right, so this is a generic algorithm. We could write this ourselves for integers, no problem. We'd write the same, this would be int A, int B, while B not equal to 0. We'll have an int T is equal to B. Well, B is equal to A mod B. A is equal to T. That'll keep running, keep running, keep running. As soon as B hits 0, we'll return the current value of A, which is the greatest common divisor of A and B. Then we can use that value that was returned to divide A and divide B, the originals, to get the reduced fraction. That makes sense? So that is what this is doing. It's just an implementation of that algorithm. And we saw it's ridiculously faster, correct? It went from who knows when this will end to, oh, that seemed instantaneous. All right, now, just real quick. Let's see if my app from years ago supports this. Okay, so we have 278. Have to walk through this to keep track. 278080 938 271 033 2215 0330 3509 6856 0276 7972. Oh, uh-oh. I typed in the wrong number and I thought that was a delete button. Totally not a delete button. All right, I won't make that mistake again. 27808 08. Oh, just a giant number?
Yeah.
All right.
It's not necessary.
How many numbers do we have to have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 122, 123, 124, 125, 126, 127, 128, 129, 130, 131, 132, 133, 134, 135, 136, 53. Okay, we have a 53-digit number now entered in. So I'm going to submit. Make sure my... All right, okay, so I can read this. 54 sextillion, 672... Okay, but we should hear my, my awesome voice from years ago. It's processing.
You changed any code in that, or is
I wrote it like 8 years ago or 9 years ago, just sitting out there. That was like one of my first apps I just wrote for the App Store to try it. Here, while it's so this is 54 sextillion, 672 quindecillion, 134 quadrodecillion, 679 tridecillion, 458 duodecillion, 243 undecillion, 160 decillion, 246 nonillion, 597 octillion, 845 septillion, 126 sextillion, 497 quintillion, 851 quadrillion, 305 trillion, 649 billion, 785 million, 421,987. That's what that number is.
not even so much money in the world.
So I guess we'll just let that keep
What
cooking.
is it, big numbers?
Huh?
What is it called?
Yeah, it's called Big Number.
Big numbers?
Yeah, so it's for iPhone only. It's from Michael Lippman Experience.
What is the maximum digit it
There
supports?
it is.
I think it supports anything. I read it as a...
4 sextillion.
Oh, come on,
Wait, stop.
you got this.
4
Processing.
Big number.
No, it's
4
it's probably somewhat buggy.
50
You should optimize the algorithm.
I don't even have the source code anymore. I'm sure that got deleted 7 years ago. All right. So, questions about any of this stuff?
I have a question.
Go ahead.
What does the arrow holds for the big integer array?
Oh, like how is big integer? How does it hold the number? It uses something called a linked list.
Is
So
it-
for those of
no,
you
I
who
mean-
take the 537 class, we talk about linked lists in there.
I mean the arrow
4
in the array. Is it a pointer?
Okay, so you mean like up here,
X0
big
or-
integer f? So, okay, I get what you're saying. It's this. So if this is f, f holds a pointer up to memory. This guy's actually a big integer. All right? But a big integer is an object. So this memory address actually holds another memory address. And that other memory address is where the actual big integer lives. Okay? And it actually it's worse than that. So f is an array, correct? This is an array of big integers. So this guy is a big integer array called f. It has 2 elements in it, right? So let's say it holds memory address 55, and that's going to take us right here. So at memory address 55, we are going to have our big integer array called f. Well, big integer array is actually an array up here, so we're going to have let's see, let's just say this is memory address 30. Actually, I'm lying. Let's say this is memory address 55. And size of a memory address in our modern language, let's say it's 64 bits. Okay, so 64 divided by 8 gives us 8 bytes. So that's 55 and 63. This is bucket 0, this is bucket 1. All right, so let's just get rid of some of this extra crap because it'll just confuse this stuff here. All right, so big integer f holds the memory address, which points to the front of this array. This array is that memory address 55 and memory address 63. Okay, now the contents of this array, though, are going to be other memory addresses. This is 31, let's say, and this is 94. So this guy here points to memory address 31 out here in memory somewhere. And at that memory address, a real big integer lives. Similarly, at memory address 94, somewhere else in memory, oh, come on, I can't click it. This guy points to this place in memory, which actually has a real big integer. All right, so we have a pointer which points to an array, the contents of which are pointers. So this is an array of pointers. That make sense? So this is the memory address of the first big integer in the array. This is the memory address of the second big integer of the array. So this big integer actually lives here, where if we follow that pointer, that's where the actual big integer is. This big integer actually lives here, so we follow that pointer, that's where it is. So it's actually a double pointer. To get to our big integer here, we first go to our array, then we follow the next pointer to that guy. To get to our big integer here, we go to our array, we walk to bucket 1, follow that pointer to this guy. That makes sense? So that's because objects are represented as pointers. All right, any other questions about the homework and how big integers and time complexity stuff works? So hopefully we kind of appreciate how much faster using the greatest common divisor algorithm was than using our hard-coded method, which seemed functionally fine, right? Functionally, it was fine. It would have worked, given enough time. Given enough time, it would have eventually finished. Probably don't want to run on battery life. Just plug that laptop in. Make sense? All right, just as an experiment, I'll go ahead and we'll do our reduce, the other version of our reduce, the one that takes forever, and I'll get this running. And we'll leave it cooking during break. Okay? So let's go ahead and let's take about 20 minutes. We'll come back at 8:20 and we'll see that this guy is likely not done. Okay, I don't think he'll be done by 8:20. All right, now I'll stop the recording.